Africa had been boycotted because of their apartheid political points of view and were cut off from fuels from the rest of the world. What they did have was a large supply of coal. So they utilized 80 fixed bed reactors to produce approximately 160,000 barrels per day of fuel. Now, the interesting thing is what keeps this plant, and this is a picture of one of the facilities right here. What keeps this plant profitable is not the sale of fuel, but the sale of chemicals that they make along with the fuels to the European Union. It requires a catalyst, iron, nickel, or cobalt. In South Africa, they use iron. Nickel and cobalt give you a different product swing and help with some of the product selectivity. However, they're very expensive. And the overall reaction is the hydrogen plus the carbon monoxide produces your hydrocarbon and water. We can also make synthetic fuels from biomaterial. About 10% of the content of the standard gasoline you get at the pump, the 87 octane, is ethanol. And that's derived from biomass materials such as corn, sorry. And it's considered a drop-in fuel. It's easily blended with petroleum fuels such as diesel, heating oil, and gasoline. It can be also used directly. Ethanol has a very high octane number, over 110.
Okay.
Using ethanol and biodiesel reduces the consumption of gasoline and diesel on the vehicle. However, you got to take into account that you're using fossil fuels to drive the tractors, to plant the seeds, to reap them, and to run the plant. They're also cleaner burner than pure gasoline. So ethanol and biodiesel manufacture. Ethanol, it's an alcohol made from sugars. You can use other feedstocks such as sugar cane, sugar beets, potato skins, rice, yard clippings, tree bark, and switchgrass. They could all be fermented. Essentially, they're making beer from this. It's the same process as used in making beer and alcohol for consumption, except that they're doing it to make pure ethanol. Biodiesel is manufactured mainly from waste oils and animal fats, and some recycled restaurant grease. It burns with few modifications. It says no, but you actually do need to slightly modify your diesel engine to run these. The rubber and the O-rings and everything have to be changed to be compatible with biodiesel. The latest generation of diesel engines being produced today, this has been taken care of because they mix biodiesel in with the conventional diesel fuel. And biodiesel is very similar to conventional diesel. The image here on the left is conventional diesel, long straight chain hydrocarbon, and the one on the right is biodiesel. And the differences are here. The methyl group at the terminus end of the biodiesel or the conventional diesel is replaced with an acetyl group in the biodiesel. Let's talk about synthesis of ethanol for a minute. The reaction that most people see is you take glucose, C6H12O6, and you produce 2 ethanols and 2 CO2s, which is all well and good. However, that is not the reaction that occurs. You're not starting with a simple sugar, such as glucose. You're starting with a polysaccharide, such as sucrose or fructose. And this involves a 4-step process where this polysaccharide is reacted with an enzyme, broken down into the glucose. The glucose is then reacted with more enzymes to produce pyruvic acid, acid acetal, and finally your ethanol. It's a long process. It does not happen overnight. So-called second generation biodiesels are used from non-food stocks, essentially any agricultural waste product. And the main routes for converting these are still being developed, but they all involve some form of heat. You're taking your biomass and you're heating it, and you're producing your hydrogen, your CO, and your CO2, plus a range of byproducts, some of which are not wanted, char and tar. Each of these processes, as I said, is a thermal process. So you're putting a lot of energy into heat. That energy has to come from somewhere. Usually it comes from combusting some of your starting material. One of the ones I was involved studying in my group when I was a division director was microalgae to alkane-based fuels. In this case, algae love to grow. You see them on top of ponds and everything. It's a non-food source. It produces a drop-in replacement fuel. It avoids potential chemical property conflicts of biodiesels. And it also produces a lot of glycerin. Glycerin is used in soap manufacturing. What you do is you start growing the algae, and at some point you stress it. That is, you deprive it of light or nutrient or oxygen, and it starts to produce fats when it's under stress, much like humans. So you form these triglycerides. These triglycerides can be broken using methanol and produce these methyl esters. And as I said, these methyl esters are direct drop-ins for fuels. However, this is very slow. We're talking microalgae, and it uses vast quantities of water and fertilizer to keep it going. Not to mention vast quantities of area, land. Let's move on to hydrogen. What is hydrogen? It's a gas at room temperature. It's the most abundant element in the universe. On Earth, its most abundant form is water, H2O. 1 kilogram of hydrogen has the same energy content as 1 gallon of gasoline. However, we don't produce it from water. We produce it from the decomposition of hydrogen-rich organic compounds. So, there are 4 types of hydrogen that people talk about: brown, gray, blue, and green. And the color has nothing to do with the hydrogen itself. It has to do with how it was produced. Brown hydrogen is produced from coal. Gray hydrogen is produced from natural gas, both without carbon capture and storage. They produce hydrogen at about $1.50 a kilogram. If you include carbon capture and storage with natural gas and coal, you get what's known as blue hydrogen, which sells for about $2 a kilogram. If you want to make your hydrogen from bio-waste, it's still blue because the biomaterial is captured the CO2 for you before you process it, but that costs about $3 a kilogram. If you want to produce it from water, you have to do it by direct water splitting, high temperature electrolysis, or low temperature electrolysis, all except for direct solar requiring electricity. And that produces hydrogen at about $6 per kilogram. So how is 95% of the hydrogen produced industrially in the world? It's produced gray. It requires the reforming of methane with high temperature steam, 700 to 1000 centigrade, under pressure, 43 to 362 PSI, in the presence of a nickel catalyst. This process is endothermic, so you got to put a lot of energy into it to make it happen. And it produces a large carbon footprint. For every 10 tons of CO2 produced, you only get 1 ton of hydrogen out. So how else can we produce hydrogen? Well, I mentioned steam reforming. And what I want to point out is everything I'm mentioning here, again, is an equilibrium. These reactions go both ways. You can do partial oxidation. That's an incomplete burn, produce CO and hydrogen. Again, you have to add heat. You can do the water gas shift reaction, where you take your carbon monoxide that you produced up here, react it with water to produce CO2 and more hydrogen. Again, it requires heat. This is very kinetically limited. This has low selectivity to CO and hydrogen. All of these require a metal catalyst, and usually it's a nickel or cobalt catalyst. not cheap. They all fall under Le Chatelier's principle, which states that when you have more compounds on the product side than you do on the reactant side, the reaction is going to want to go towards the reactants. So in these two cases, we're producing 3 molecules here, 4 molecules here, and we're starting out with 2 and 1.5 here. So these reactions are going to want to stay as methane. And the same data I told before, to 10 tons in another method format is if you produce 1 million standard cubic feet of hydrogen, you'll make 13 metric tons of CO2 by any of these processes. There's one other process, and it's been under study since the 70s. It's called dry reforming. Yes. Nope. Under dry reforming, you react methane and CO2.
Advertisement.
You react methane and CO2 to produce carbon monoxide and hydrogen.
I didn't see his balance.
Somebody mute, please. The process consumes 22 tons of CO2 for every ton of hydrogen.
I don't see his balance. Oh, established creditor balance, established settlement. That's all bullshit, freak. It's an ad.
Excuse me.
Yeah, but I'm sure he owes more than $40,000, so it's all bullshit.
Dr. Taylor, I'm trying to get a hold of this guy to
Yeah.
Sorry about that. You can we'll just 1 second.
Yeah, sure.
Goodbye.
Mr. Rosenberg, please mute yourself.
He's now muted, Dr. Taylor. You should be good to continue.
Okay, thank you. Well, contrary to what you heard, I'm not selling anything. I'm explaining what is out there in the technology today. This is the newest technology that's available right now for dry reforming. It's consuming 22 tons of CO2 for every ton of hydrogen produced. However, if you look at it, this is the reactor itself. Put that in scale, this is probably about 8 inches tall. And you have to use microwaves to get it to work. So you're putting a lot of energy into generating the microwaves in order to get this reaction to go. So this is far from commercial. And as I mentioned at the beginning, this has been going on since the 70s. I've been involved in it since the 80s. So what's the government doing now to push hydrogen production? They've set up a 5-phase program for decarbonization and hydrogen production. Because of COVID, these dates have pushed back a little bit. They don't have a newer slide available on their website. So this date now is 2022, but it looks at targeting clients who in the industry would be interested in working with the government to make this happen. After that, bring in other investors. And finally, bring it to industry and start building pilot plants by 2030. One of the things that the DOE does is you have to put money in to be part of the players. Depending on how new or how uncertain the technology is, depending on how much you put in. But typically there is a cost share on all of these things. So do we really need blue or green hydrogen? If we're going to go to the hydrogen economy, yes. So DOE announced the hydrogen shot. This is part of the Energy Earthshots initiative, and it's designed to reduce the cost of clean hydrogen. And their goal is to make 1 kilogram of hydrogen at $1 per kilogram in the next decade. Right now, this is a third less than what can be produced by dirty hydrogen, and 6 times less what can be produced by green hydrogen. So it is a real hydrogen shot. So let's say we do the hydrogen. How do we transport it? It's a gas. We can do it by pipeline. However, there's very limited amount of pipeline available for hydrogen delivery. Most of it is in the Gulf Coast because it's used in refinery of oil to help hydrogenate it and make it thinner for other products. You use high pressure tube trailers, but then you're not transporting a whole lot. And that's only good for about 200 miles or less. You could liquefy it, but that's expensive. And also it evaporates, it boils off, which is not good. You can burn hydrogen, as I said, directly in an internal combustion engine. This is first done in 1806. It's a very simple reaction. Hydrogen plus oxygen forms water. Very green, very clean. However, since air contains nitrogen, you're going to form nitrogen oxides. So you need to have some kind of control on the engine to control this. You also need to modify the engines. You just can't take your standard internal combustion engine and switch from gasoline to hydrogen. You need hardened valves and valve seats, stronger connecting rods, non-platinum tipped spark plugs, because the hydrogen will go into the platinum and embrittle it, a higher voltage ignition coil, fuel injectors, etc. There's a whole series of things that you need to do. But these are two marine engines that are available for sale that run on hydrogen. So hydrogen can also be used in turbines. This has been done since 1937. There are actually two commercial plants running that are producing electricity by a process called integrated gasification combined cycle systems, where you take coal, you turn it to synthesis gas, and you convert some of the CO into more hydrogen, and you run those through a turbine to generate electricity. Again, you need stringent NOx controls. And state-of-the-art engines, you need the premix to control this NOx. What's under development are new types of turbines, and this is one system here. Again, it's a combustor that actually exists. It is run, then it's modeled using software. You get a feedback loop here. You run the combustor, you get the data, you run the model, you compare the data. You see where the data's off, and you adjust it. You adjust your software to make it work. This has been done enough that at atmospheric pressure, they get good agreement between what they see coming out of the turbine and what the model produces. You can also use hydrogen to generate electricity directly in a fuel cell. It's essentially a controlled oxidation, but instead of a lot of heat, you're producing electrons. You feed the hydrogen in one side through the anode, it reacts with a catalyst. It's separating the protons and electrons. The electrons go through the loop to make the work. They react with air on the other side to produce water. Fuel cells are classified by their source of electrolyte that they employ. There's polymer electric membranes, direct methanol fuel cells, alkaline fuel cells, phosphoric acid fuel cells, molten carbonate fuel cells, solid oxide fuel cells, and reversible fuel cells. Each of these has their advantages and their challenges. What I really want to point out here is if you notice this particular column right here that I'm highlighting, that's the efficiency of the fuel cell, and they all run between 40 and 60%. However, most of them tend to require high temperatures or corrosive materials, expensive catalysts, sensitive to impurities. So what was it going to cost to go to a hydrogen economy? I can't actually see my title here because the bar's covering it. But it's going to take about $1 to $1.4 trillion of US investment between now and 2030, or between 2030 and 2050. And the majority of this investment must be made on land to get the infrastructure in place. In 2019, the presiding principals set up a bank as a framework for financing this. They set a series of targeted goals to meet it, and most of their signatories failed to meet the goal, first report's goal. The shipping industry is looking to create its own $5 billion climate research fund, and it's going to be financed by a $2 per ton charge on marine fuel. Now, this has not been approved, mainly because of the high price of fuel lately because of everything going on in the world. But if approved, this would be the world's first mandatory global carbon levy, according to the World Bank. Nuclear power is particularly suitable for vessels, which need to be sea long time without refueling. Currently, there's over 160 ships powered by more than 200 small nuclear reactors afloat today. Most are submarines, but that also includes some icebreakers and aircraft carriers. The constraints being imposed on fossil fuels may bring nuclear propulsion into more wide use. To date, though, exaggerated fears about safety have caused political restrictions on getting access to ports for most of these vessels. Now, nuclear propulsion in marine has been used since the 1940s, and the first test reactor was set up in the US in 1953. In 1955, the USS Nautilus, the first nuclear-powered submarine, was put out to sea. Most people picture a nuclear reactor as something like 3 Mile Island or Chernobyl. What we're looking to go to is what's called small modular reactors, or SMRs. Now, these SMRs have many advantages over the traditional nuclear reactor in that they have relatively small physical footprints. They have much reduced capital investment. They can be situated in locations that it's not possible to build a large nuclear power plant. They have provisions for incremental power additions. Since they're modular, it's like adding extra batteries to a system. If you need more power, you put another unit in. They have higher efficiencies than a traditional plant. They don't have pumps moving the water around to keep the reactor cores cool. So if there's a power failure or a pump failure, can't be a pump failure because they don't need them. And the design is much simpler than a standard reactor. So how does this work? Well, we take a heavy element such as uranium or plutonium. We use their radioactive isotopes, and we send a neutron into it. It slams into the uranium or plutonium and splits it into two, releasing a large amount of thermal energy. Great. However, you still got to deal with the byproducts, which is an issue that has not been fully addressed at this point in time. There we go. So how do we power the ship with the nuclear reactor? It's easy. Right now, most ships are using a generating steam, which run steam turbines. This is all the same as a conventional steam turbine in the propulsion room of a ship. It's just that we're replacing the boiler and the fuel source with a reactor. This nuclear reactor generates heat. The heat is exchanged through a steam generator. The steam generator runs the turbines, which drive the shafts and the propeller. They also power the batteries and the electricity for the ship. So the U.S. Nuclear Regulatory Commission has recently issued its final safety evaluation report. When I gave this talk last year, it said it was supposed to be certified by the end of 2021. Well, I checked yesterday, it still has not been certified. They're now saying by the end of 2022. We'll have to wait and see. So this was a result of $400 million in funding by DOE since 2014 to bring in the help with the development of these SMRs. And the NRC is changing the rules to certify the new school SMR design. Once certified, they will be able to join 6 other light water reactor designs that are being tested by the NRC, and hopefully a selection will be made there of a standard type SMR. Are there any SMRs in use today? Yes, mainly by the Russian Federation and China, and they're used as floating power plants. They produce a modest amount of power, between 6 and 325 megawatts electric. The plants are intended to produce power in areas where there is no thermal or electric power available, and it's not practical to either build a large fossil fuel plant or to build a nuclear plant. So what can the future hold? Well, if we have carbon-free electron sources, again, geothermal, solar, wind, hydro, nuclear, or fossil fuel carbon capture and storage, we can produce electrons. With these electrons, we can do whatever we want. We can use it for electric power, for charging stations, for vehicles, over-the-road trucks, for trains. We can use it for fuel production, for hydrogen production. We can use the hydrogen in almost any vehicle. The fuels, of course, can be run in any vehicles. We can make chemicals. We can also capture the CO2 from the air or from these processes and run it back through the cycle to make more fuels and more chemicals. So in summary, fossil fuels can be replaced by alternative fuels. The technology exists today, and it's existed for a long time. But there's many hurdles that need to be overcome. The major one is cost. Right now, VLS MGO on a world market price is running between $650 and $820 a ton. Comparison, if you want the target for hydrogen fuel, it's $4,000 a ton. Alternative fuels are much higher than this. You got to worry about the energy density. You got to come up with a method of distribution storage. You need to decarbonize. And for many of these alternative fuels, you need special materials. So the point I want to bring across is, yes, alternative fuels are available today, but there's a lot of additional research that's needed to advance these fuels. There's a list of the references. And with that, I will conclude. Thank you, and open it up for questions.
Thank you, Dr. Taylor. I have a few questions that have been placed on the chat. If you
Okay.
don't mind, I'll start. Let me start with the first one because it's in the beginning of the presentation. How would the government build the devices necessary for the removal of CO2 from the atmosphere without causing the gaseous makeup of the atmosphere to change, causing the world population to slowly suffocate?
Okay. I actually had a very similar question to this when I gave a talk in Istanbul about 10 years ago. If you look at the concentrations of the gases we're removing from the atmosphere, that is the carbon dioxide, I mentioned it was 0.041%. What we need to survive here on Earth is oxygen. The nitrogen's a diluent, it's there, but we don't consume it. So by removing the CO2 from the atmosphere and storing it, we're not going to have any impact on the humans. There's going to be still plenty of CO2 in the atmosphere for the crops to grow, for the phytoplankton to use in the ocean, et cetera, for the algae to use. So what they're looking to do is take it back to a level of CO2 somewhere around the start of the industrial era, which I believe is about 250 parts per million, or 0.025%. So essentially cut the CO2 in the atmosphere almost in half. I hope that answered the question.
All right, the next question, we start to get a series of questions about the nuclear power. What is the most
Okay.
common isotope used in a nuclear fuel reactor?
That would be uranium-235.
Could the byproducts created from nuclear reactors be used through through reconditioning, like how steam is used in the steam cycle?
Yeah, there are things called breeder reactors, which actually generate another radioactive element that's got even a higher potential for energy use than others. Most of the spent nuclear material, though, is given off low energy particles that are very hard to capture and utilize for anything. And they do not give off a lot of heat. So it's not that easy to reutilize the spent material. Right now, it's being stored underground or under the ocean.
Was that outlawed during the, recycling the nuclear products outlawed during the Carter administration? Trying to think. I'm
Be honest,
stating
I
my
don't
age here, which is your age also.
Yeah, I honestly don't remember.
Right. Which type of hydrogen fuel cell do you think would be the easiest to transition to with our current reliance on gasoline and the financial difficulties ahead, is there one that is easiest to introduce today?
Yes, and it's already been introduced. It's the proton exchange membrane, PEM. The polymer electrolyte membrane or proton exchange membrane. It goes by both names. They've been used to power golf carts, lawnmowers. I've actually driven a SUV that was powered by one.
Just a note, we have on campus, at the moment, we still have it, I believe, the first hydrogen-powered house.
Oh, it uses a fuel cell.
It used a fuel cell and it used solar heat for hot water.
Uh-huh.
It was pretty cool. It was pretty efficient. We had it down on the National Mall during competition, probably about 10.
Oh, I remember that. Yes.
Yeah.
Yes, I was down there.
Yeah.
But as I said, the PEM fuel cell, if you notice, it operates at a relatively low temperature, less than 120 degrees centigrade. And it does not contain any corrosive or really cost prohibitive materials.
Let's see, will the byproducts from the nuclear reactor cause more harm to the environment than the actual carbon being emitted from a standard diesel engine?
If properly
Good question.
stored and the storage facility maintained, no. I mean, we've been transporting nuclear material around the world in this country for 70 years, almost. In fact, the fuel being used in our nuclear reactors now is coming from spent Russian nuclear warheads. So that's being shipped from Russia to the US.
That's great.
What the main problem is with the carbon dioxide is if it is the leading cause of global warming, then that is causing more damage than a little bit of radiation that might escape. I mean, we're exposed to radiation every day. And we have ways of storing it safely. France, and I don't know if it's currently true or not, but at least a decade ago, 90% of their electricity was produced from nuclear reactors. And they are very, very expert in the storage, handling, and monitoring of these spent fuels.
Let's see. Why does patent pending technology need to use microwaves? I'm not quite sure I understand that question.
Okay, I mentioned that energy barrier. If let me go back to that slide. There we go. We're starting with CO2 and methane instead of water. Methane also is a relatively chemically inert material. It takes 104 kcals per mole to break that first carbon hydrogen bond. So you need to push that up over this hump here. In order to do that, you need to supply energy. In this case, they're using microwave energy, mainly because it's providing the energy without providing the excess heat so that we get the products that we want and not a lot of byproducts.
This is a really good question. It's on my mind. In your opinion, what type of decarbonizing fuel should the shipping companies adopt?
That's an excellent question. And I have thought about it. Right now, the very low sulfur fuel oil is the best alternative. To switch, to transition, let me go back here to the, here we go, types of fuels. Liquefied natural gas has been used to propel ships for a long time. All the LNG that's shipped around the world, most of those ships use the boil off from the LNG to power their ships. However, it takes up a lot of space. You would want a liquid, my personal opinion is you want a liquid fuel. You want a liquid fuel with a high energy density. So you'd want a biofuel or a synthetic fuel, such as one made by Fischer-Tropsch. That's a drop-in fuel. least expensive, easiest to use. And if these are made at a large facility with carbon capture technology, you can capture the carbon used to produce them at that source point. Eventually, I would like to see hydrogen powered. I've been a big proponent of hydrogen, and I've always been a proponent of nuclear.
I know I've been reading the trades. I've been seeing some move towards methanol licensing or some contracting being taken place with methanol burning.
Right.
So,
Yeah, methanol is interesting. It is a liquid at room temperature. It's made by syngas again. So you're taking either your methane or your coal, you're converting the CO and hydrogen, and then you're reacting it to make your methanol over a nickel catalyst. It's less energy dense. It's also toxic. Methanol poisoning, people drinking wood alcohol, methanol, thinking it was real alcohol, go blind, or it destroys their liver. Even the vapors, if you breathe it, can be deadly. So
I know during the 70s when when Sealand was trying to build the SL7s, which were today some of the fastest large ships around, they had considered nuclear. And the biggest obstacle was where can we go with it? Germany had said you can go there. A lot of the problems were in the United States. They didn't want to accept nuclear, but the ships were actually designed that way. Those ships have been clocked at 38 knots on burning fuel oil. They would probably still be using them, if I would imagine, if there were nuclear plants, you know.
right, and that was one of the things I mentioned in when I was talking about the nuclear, is that a lot of ports will not let them in.
Right. Even Japan at one time wouldn't take a nuclear aircraft carrier.
Exactly.
Right.
Yeah.
Let's see, aside from the cost implications of conversion to hydrogen fuel or nuclear power, what do you estimate to be the implications in training for us, future marine engineers? Good question.
Yeah, good choice.
Each point will be a 6-year program. Everybody raise your hand. You want to stay? I'm sorry, go ahead, Chuck.
Okay. There's going to be during your career time, which is probably going to be another 30 to 40 years, let's say. And I know that sounds like a long time, but the captain and I can tell you that it'll go by real fast. You're going to be at the transition from the conventional fuels into the newer fuels. So an understanding of the chemistry, of the engineering required to do this type of transition is going to be important, because while the generation of propulsion is either going to be still electric or steam turbines turning shafts, how you get that energy to be electric or steam is going to be different. So there's a lot of new materials that are going to have to be designed and come up with. There's going to be also in the ship's design itself. Right now, you put your big diesel engines at the lowest level of the ship, correct?
Right.
For ballast and weight. Well, when you have other fuels that don't require anything that heavy, you got to figure where you're going to put those too. You also have to figure too is a lot of these alternative fuels, because of their low energy density, if you're going to use them in a ship, it's going to take up a lot more volume. So how do you sacrifice, or how do you come to a compromise between how much you can haul and how much fuel you can carry? So yeah, again, that's ship design.
Right. Let's see, from Mr. Marengo. With the reliance on diesel and gasoline so high, is there any kind of future towards development of alternative fuel sources?
That's a tough one, because right now we consume a lot of petroleum. In the US, we don't import, I'm sorry, let me correct that. we consume about 22 million barrels of petroleum a day. At the height, we were actually producing 14 million barrels a day and importing 8. Now it's about 50-50. So that is a lot of product that you have to displace. Pumping oil out of the ground, putting it in a ship, shipping it halfway around the world, and refining it is over a century-old technology. It's been very well matured. And you're going to have to find something that is going to be almost as relatively cheap as petroleum. And that's not easy because they can pump petroleum out of the ground in Saudi Arabia for about $12 a barrel. It costs another $1 or $2 a barrel to put it in a ship and send it over to port in Texas. So that is very inexpensive. And each barrel of oil, 42 gallons, gives you 38 gallons of gasoline, gives you about 16 gallons of diesel. So, I mean, that is very hard to beat. So unless there is a mandate that requires you to switch, it's going to be hard. Plus, there's political ramifications too. I mean, one party comes in and they say, let's open up the wilderness and let's start drilling. The next party comes in and says, well, we're shutting down the Alaska wilderness and we're going to use wind and solar. So, you know, that all plays into it also.
Thank you for that answer. That was very insightful. Outside of nuclear and hydrogen power, are there any other viable alternatives currently being considered which would take on the workload of internal combustion engines on ships, on vessels?
Yes. Liquefied natural gas is one.
Yeah.
I actually developed a process. It's, I think 2 of my patents cover it, where you use gas hydrants. And essentially what you're doing is you're storing the natural gas inside a crystal of water ice. And it has about the same density energy wise as compressed natural gas, but you don't have to compress it to high pressures and you don't have to keep it stored at low temperatures. We considered that for a while. We talked to several maritime organizations about that. Let's see, the synthetic fuels. We've worked with the Defense Logistics Agency. I believe that's the fuel supplier for the military. And we worked with the Air Force on using synthetic fuels. And as I mentioned before, the nice thing about synthetic fuels is they're drop-in. You can ship them in the existing pipelines, you can store them in the existing tanks, and you can pump them right into the motors.
Let's see. How feasible is it to replace fossil fuels entirely with nuclear or alternative biofuels in the near future?
Well, near future is relative. In the future, I would say it's very, very possible. I will not live to see it. My son may, your students may. Again, like I said, it's the infrastructure and the cost. Once you start going to these materials that cost 4 times the cost of fuel oil, then that adds to the cost of shipping, that adds to the cost of the product, and that leads to inflation. And that's gonna, you know, once it starts hitting people's pocketbooks, that's when they start screaming. There are breakthroughs that need to be made. And I think that those breakthroughs are coming, but I don't think that they're coming in the next 20 to 30 years, to be honest with you.
Here's one about nuke. Why are U-235 reactors used and not thorium reactors, where there is more thorium present in the Earth's crust? The reactors are safer to use and it produces less byproducts.
I honestly don't have an answer to that. The only thing I could suggest is that the thorium might be harder to refine than the uranium.
I'll give a nuke semi-experienced answer as well. It has to do with energy density. So if someone wants to come and talk, we can talk about energy density on the 180 of 200 nuclear powered vessels of submarines in my office anytime. Peter Seth Hall, room 128.
Here you go.
Thank
Get the
you.
nuclear engineer, I gotta ask him. All right. Early on in your presentation, you discussed the synthesis of ethanol from agricultural waste and the use of
Yes.
biofuels. In your professional opinion, what is the feasibility of this on a larger scale within the maritime industry?
Very good. We've looked at this when I was employed at the DOE. Again, I did most of my work with the Air Force because we were building a pilot facility at Wright-Patterson Air Force Base to produce synthetic fuels for jets. And we actually were able to run a commercial jet on 50% synthetic fuel and 50% petroleum derived fuel. And it was certified by the FAA. The problem here again is if you're doing it from biomaterial, if you're doing it by fermentation, it's a very slow process. It's a energy intensive process. I mean, when this was first beginning, it took, for every barrel of oil displaced by ethanol fermentation, you used 1.5 barrels of oil. Now that number has come down to almost 1 to 1 now, but you're just taking the source and moving it to another location.
Right.
Also, you get into impact on people's food. I don't know if anybody's noticed the price of corn lately, but because it's mandated to go into gasoline at 10%, the price of corn is through the roof. Farmers use it for feedstock for cattle, which raises the price of meat, etc. So it's a chain reaction.
Right. And I believe there's some issue over mowing down other carbon dioxide consuming crops to put up corn, and the process of plowing under trees and forests and so forth causes a lot of CO2 in the atmosphere.
Exactly. Exactly.
What's coming up? What are coming up options are there for disposing of nuclear reactor fuels?
To be honest, I have not seen anything in the last 10 years that's new. I mean, they've looked at storing it in Yucca Mountain out in the western deserts. I mentioned that France stores theirs under the ocean. People looked at storing it in mined out salt mines. But all the technology right now requires it to be stored somewhere, and it be a burden on a future generation to either keep monitoring it and keep it safe from the environment, or to find a use for it. Unfortunately, that's the best answer I have for it.
In your opinion, what is the biggest disadvantage to SMRs? Would certain countries benefit more or less? Also, in the future, do you see the shipping industry transforming towards electric ships?
3 good questions.
Yeah.
Personally, as I said, for the last 30 plus years, I've been pushing SMRs. I think they would be great. They could be used to displace a lot of fossil fuel power plants. They could be used on ships, especially ships that need to be out. Imagine you only have to refuel your ship once every 10 years. Great. I know most of the refueling is done while you're in port, unloading and loading, but still. I lost track of the other 2 questions on that part. Could you repeat those for me, please?
Let's see. Would certain countries benefit more or less?
Okay. The United States would definitely benefit. I mean, European countries, France is already making full use of nuclear power. Japan was heavily reliant on it. So was Korea before the incident with the Fukushima reactor. Germany also. Germany has put a ban on burning coal, and they've also shut down their nuclear power plants. but they haven't come up with a solution as to where they're going to get their electricity from. Reminds me of California. But yeah, there are certain countries, especially if you're looking at third world countries, if you have to put the infrastructure into a third world country to bring electricity in, putting a SMR in would greatly help. And I like to equate this to the example of the use of the cell phone. No country in the world today is putting up telephone poles and telephone lines and hardwiring for phones. Even third world countries have gone to cell phones. Why? You put up one tower for every so many square miles and everybody has self-service. So I like to think of CMRs as doing the same, or SMRs doing the same thing.
Do you see the shipping industry transforming towards electric ships?
I actually do. At some point in the future, beyond this 2050 timeframe, I see them. If you look, a lot of ships today are powered electric. How they get the electricity to power their thrusters is different. That's where the difference will be. But yes, I mean, a lot of ships that have those azimuth pods on them and bow thrusters, and they're all electrically powered.
Students, if you're interested, go and Google up fleetzero.com. There's a handful of Kings Point graduates putting together an electric container ship company. Fleetzero.com. We're hoping to have them give a presentation also in the future.
Oh, very interesting.
Yeah, they were class of 11, 12, and about that era. So they've been out in the industry for quite a while.
Mhm.
And they're looking for financing. They all went to business school and engineering school, and they were in the petroleum industry of all things.
Oh, okay.
Yeah.
Okay.
Given
very
that LNG tankers manage LNG boil off by burning the boil off methane gases as fuel, how practical would it be for the potential liquefied hydrogen tankers to, as mentioned in the presentation? Interesting idea.
Actually, probably the exact same thing. And hydrogen boils off much quicker than liquefied natural gas. So yeah, I would say that. But again, if you're burning your commodity that you're transporting to market, you're losing value. So you got to do a cost comparison. Is it less expensive to burn the hydrogen that you're going to lose anyway, which it probably helps? And is there enough boil off to power your vessel?
Let's see, I'm going to pick off the longer ones and maybe we can get, there's a lot of questions. Are you familiar with the uptake and release of hydrogen into or from lithium hydride? Seems
Yes.
like a great form of storage for hydrogen-powered road vehicles since the rate of release can be governed by the heat from the vehicle's exhaust. Additionally,
Exactly.
the hydrogen can be hydrolyzed at the vehicle owner's home. What's your opinion of hydrogen via lithium hydride as an alternative fuel source?
We've looked at that. The capacity of the lithium hydride to hold enough hydrogen was the issue when we looked at this about 15 years ago. And to be honest, I have not kept up to date since then on if there's been any advances. I know that they've been looking at Z-lights for storing hydrogen. They've been looking at metal oxide material, perovskites for storing of hydrogen. But then again, since hydrogen is such a light material, the substance that you're absorbing into is so much heavier that you're not getting very high energy densities out of it.
Let's see. I know some people would be angry with me if I skip over them. How long until projects come into effect fully everywhere after being approved? In other words, what's the approval process look like? Also, how long are all these projects projected to last, and are they cost efficient in the long run, even though it's expensive right now?
Okay. The way I can tell you the way DOE works, we put out what's called an RFP, a request for proposals. We will say, we want to look at enhance hydrogen production, and we set the goals at $1 per kilogram in the next decade. People come back in with proposals. The proposals are reviewed, and typically, since we're funded by Congress, the money has to be spent in the year that it's allocated. Now, some of the money is allocated for 3 to 5 years, and that's typically the life that we use for the project to get from the experimental stage to the pilot stage. If it goes to the pilot stage, it's typically another 5 to 10 years before we get to a commercial stage product. So now you're talking 15 years. And a commercial product, once it's approved, if you don't already have the facility, you have to build a facility. So I'm going to tell you it's going to take about 20 years. I can tell you I started working on a process for converting methane into gasoline in 1985. We built the pilot plant in 1995, and we shelved the product in 2002. And that's a typical life expectancy.
Let's see, we have a question from the great class of 69. There is a movement to battery operated vehicles, cars, trucks, ferries, etc. In your opinion, what impact will this have on atmospheric CO2 reduction if it is adopted globally?
That's a good question. And I actually have some data here that I was meaning to put in and I forgot to. There's an MIT report out within the last year or so that I found yesterday. And it says that an 80 kilowatt lithium ion battery, which is what it's in a Tesla Model S, to produce that in China, just to make the battery, puts out as much CO2 as if you drive a similar size car 40,000 miles on gasoline. Now you have to take into account how you're going to recharge that battery. If you're recharging it from the electric grid, which is either natural gas or coal-fired in a lot of the United States, you're talking efficiencies of 38 to 40% to get that electricity into your house. You're then talking about a converter, which drops at another 5%. So you're producing a lot of CO2. A few years ago, I did a paper study, and it was never published, but I did the comparison of a Mitsubishi, I think it's or Nissan Leaf, all electric car, and a Chevy Cobalt, and what the CO2 emissions were from what's called well to wheel. That is from the time the gasoline's produced or the time the electricity is produced to the time it's consumed. And both vehicles were identical at that time about, I think I did this study about 10 or 12 years ago. Now, technology has advanced some at this point, but you still need to generate the electricity. The current administration says that we're going to get this electricity from renewables. My personal opinion is it's not going to happen that way. The sun doesn't shine at night, the wind doesn't blow steady all the way around. So it's going to be hard to not supplement that electric with fossil fuels. So even though it sounds good and a lot of people push for it, there's a lot of people that say that it's just not going to happen. And a perfect example is 3 weeks ago, the state of California said that come 2035, there will be no new internal combustion engine sales within the state. Everything's going to have to be battery electric. 1 week later, they made an announcement that please shut off your air conditioners and your fans during the heat wave because we don't have enough electricity in the grid to power your air conditioners. So how are they going to power an entire several million car fleet with electricity if they can't power the current existing fleet with our existing homes with air conditioning?
All right. Is it possible to convert coal power plants to nuclear plants? If so, are there any drawbacks to this process? How would this affect areas where coal mining is predominant, such as Appalachia?
No, it's not possible. Completely different technologies. You can convert coal-fired plants into natural gas-fired plants, which is what a lot of them have done. To bring the coal mining back, you either need to come up with a approved clean coal-fired power plant, which requires not retrofitting, but a brand new from the ground up construction. Or you need to be selling the coal to other countries which don't care if they're putting a CO2 in the atmosphere, such as China, India, etc.
So you have a question from Dr. Furlan. Thank you so much, Dr. Taylor, for such an interesting, informative, and enlightening presentation. I also have a question. Are there any CO2 capture technologies most adaptable on board ship? In particular, I like the looping idea and the use of metals and their redox reactions with carbon to convert CO2 to fuels. What are some of the challenges associated with this idea or technology?
Actually, we looked into that. My supervisor at the time I was a researcher was a reservist in the Navy. So he still had links with the Navy, and we were talking with them about this. And there were several methods of doing it. You know, one was to capture the CO2, liquefy it, and inject it into the bottom of the ocean, where it would stay a liquid at the bottom of great depths. Another one was actually put carbon capture facilities on the ship itself. Now, the problem came into the fact that these facilities use a liquid amine, similar to like ammonia, as the material that captures the CO2, and to get it back, you have to heat it to release the CO2. So when you got to port, you'd have to unload the amine, put fresh amine in, and then on at shore, it would be regenerated. The biggest drawback was the electricity usage. And let me put this in perspective of a coal-fired power plant. If you want to get to 90% carbon capture with a coal-fired power plant, and you're going to do this with a carbon capture technology we have available today, you're going to need to build, if you have 4 coal-fired power plants and you want to capture all the CO2 from them, you're going to need to build a 5th coal-fired power plant just to power the CO2 capture facility. That is, it requires 20% the output of the coal-fired power plant to power the CO2 capture and injection facility. So that's where the main problems are right now.
Right.
The injection in deep sea I actually liked, but there was a lot of questions about what happens if you have a turnover or a thermal event at the bottom of the ocean, and then all the CO2 comes up and burps.
Let's see. I think we'll ask one more question and then we'll give a closing. How do you see the methods being implemented in the future? Meaning, will companies work with governments to find the most cost-effective way to reduce CO2 emissions while maintaining engine efficiency?
Good question. A lot of companies are saying that that's what they want to do because it's the politically correct thing to say at this point in time. It comes down to bottom line. Again, companies are for profit. They have to answer to their shareholders. And if it's going to impact their profit, then they're going to be a little leery of it. This is why they're looking to the government to put a lot of the money to do this type of research. There's an old something I heard a long time ago, and I believe it's true, but I haven't been able to track the source, where the president of ExxonMobil said, do you know what ExxonMobil's #1 product is? And everybody in the audience said, fuels. He goes, no, money, making money for the shareholders. And again, that's where it comes in, is it comes down to dollars and cents.
All right, and I think I got just about everybody on the questions. We ran quite a bit over. Interesting subject, of course, and a lot of questions. If anybody else has a question, you can raise your hand or ask a verbal question if you would like to. There's a few people left. People are running off to dinner. So what I'll do is close this out, and I'll say thank you very much. We will be, I don't know that we have certificate made up yet, Jack. We will be sending out a certificate.
Absolutely, we do. You'll have a nice thing to put on your Zoom background is my joke, and I always say at these meetings. You'll have a
There we
nice
go.
background showing you where you've been to add to your rep. So thank you very much, Doctor.
Thank you. Actually, that's what my Zoom background is now. This is Lake Bella. Let's see, we'll get this straight here. Barbolino in the Italian Alps. I flew over that from Genoa to Paris a few years ago and took that out the airplane window.
This is just as exciting, so you'll have. Thank you, sir.
Thank you. I appreciate time.
All right, folks, we will get a word out there on the recording. I'm going to stop recording now. I probably did stop recording. Nope.